August 14, 1944, at 23,000 feet above Rostow, Germany, the cockpit of a Messerschmitt Bf 109G shook violently as the speed crept past 500 km/h. For years, this exact moment had been the Luftwaffe pilot's escape. Allied fighters would break off, unable to continue the dive without losing control. But on this day, something was different. The P-38 Lightning chasing close behind did not pull away. It held steady, still firing. What German pilots were witnessing was the end of their most trusted tactic. A simple but powerful American innovation had changed the rules. Electrically controlled dive recovery flaps, fitted to the P-38 Lightning. With them, U.S. pilots could now follow dives that had once been deadly to attempt. The balance of aerial combat was shifting. The P-38's dive problem had been discovered by accident back in spring 1941. During a high-speed test dive from 30,000 ft, 9,120 m, Air Corps Major Signa A. Gilkey felt the Lightning suddenly shake. At around 320 mph, 515 km/h, the nose pitched down sharply, leaving the aircraft nearly vertical. The issue was traced to shock waves forming on the wing surfaces as they neared transonic speeds. These shock waves pushed the center of pressure backward, forcing the nose down and leaving the elevators useless. The problem was confirmed in tests at the Ames Laboratory Wind Tunnel, operated by the NACA, National Advisory Committee for Aeronautics. Results showed the P-38 would hit compressibility limits in steep dives, where control authority was lost. By 1942, German intelligence had learned of this weakness through combat reports and captured pilot interrogations. The Luftwaffe quickly exploited it. Their standard maneuver became the half-split S-dive. Whenever a Bf 109 or Fw 190 wanted to escape a Lightning, the pilot would roll over, pull into a steep dive, and leave the American fighter unable to follow. Throughout 1942 and 1943, this tactic was widely used across the Luftwaffe. In combat over North Africa, reports showed German aircraft escaping successfully in most cases when the maneuver was attempted. The advantage wasn't only physical, it was psychological. P-38 pilots came to believe their opponents could always slip away. Morale suffered across Lightning squadrons in the Mediterranean and European theaters. Unknown to the Germans, Lockheed engineers had already been working on a fix. In early 1943, quick-acting dive flaps were designed and tested. Installed on the wings, just outboard of the engine nacelles, these small plates were simple but effective. When deployed, they shifted the center of lift forward, restoring elevator control. Unlike regular landing flaps, they dropped into a V-shape near mid-wing, specifically engineered to counter compressibility. Clarence Kelly Johnson, the P-38's chief designer, had recognized the danger years earlier. He raised concerns in the design phase and sought advice from leading aerodynamicists. However, NACA initially refused to conduct the needed high-speed tests, claiming it might damage their wind tunnels. This delay cost valuable time. It was Lockheed's test pilots, especially Tony LeVier and Milo Burcham, who finally proved the solution. Alternating dive tests at transonic speeds, they showed the new system worked. The flaps could deploy to 35 degrees in just 15 seconds, giving immediate pitch control even in near-vertical dives. Data confirmed the P-38 could now dive safely at far higher speeds. But combat deployment hit a major setback. Lockheed had built more than 200 retrofit kits for existing P-38 J-10LO and J-20LO aircraft already stationed in Europe. In March 1944, the transport plane carrying these kits, an American Douglas, was tragically shot down by a British RAF pilot who mistook it for a German Focke-Wulf Fw 200 Condor. The loss destroyed months of preparation and delayed the upgrade. This setback coincided with Tony LeVier's 4-month morale tour of P-38 bases. Despite the loss, Lockheed pressed on. In Burbank, California, P-38J models rolling off the line in spring 1944 were towed onto the ramp and retrofitted in the open air. By June 1944, the final 210 P-38J Lightnings left the factory with dive flaps built directly into production. LeVier's demonstrations became legendary. Taking up his modified P-38, he climbed to 25,000 ft, pointed the nose straight down, and dove in full view of skeptical pilots who expected to see him crash. Instead, he pulled out smoothly, then added low-level rolls for emphasis. Flying a specially upgraded P-38J-25LO named Snafu Perman at Lockheed's Belfast Modification Center, LeVier stunned audiences by performing maneuvers most 8th Air Force veterans considered suicidal. His flights at bases like King's Cliff erased doubts. Morale among P-38 squadrons surged, and by the summer of 1944, Luftwaffe pilots discovered their old escape maneuver no longer worked. The P-38 Lightning had finally solved its greatest weakness, and in doing so, stripped the German fighters of one of their last reliable tactics. The P-38s currently flying in the European theater of operations did not yet have the new dive flaps installed. Even so, demonstrations were held to show pilots what the coming upgrades would bring. They were told that soon they would be able to chase German fighters into steep dives and stay with them all the way down. By August 1944, the P-38 J-25LO models with factory-installed dive recovery flaps began reaching frontline squadrons. The effect on air combat was immediate. German pilots who had relied on steep dives as a sure escape now discovered that P-38s could keep up, even in maneuvers that once seemed impossible. One of the men who experienced both sides of the problem was Robin Olds, who would later become one of America's most celebrated fighter pilots. On one mission, Olds dove after an enemy aircraft in an earlier model Lightning. In his excitement, he pushed the dive too far, hitting compressibility. At lower altitude, denser air gave him back control and he managed to pull out, but the stress blew out his canopy window from the heavy G-forces. That frightening experience came in a P-38 without dive flaps. Later, after flying versions equipped with the new system, Olds immediately recognized how different the handling was during high-speed dives. The cause of compressibility was simple but dangerous. At very high speed, the center of lift shifted from the front of the wing to the rear, forcing the airplane's nose down as if it were trying to roll into an outside loop. The dive flaps corrected this by shifting lift forward again. They were controlled by a small electrical switch mounted on the control yoke. Once activated, electric motors extended the flaps in about 5 seconds. Deployment not only restored elevator authority but also gave an instant nose-up moment. Pilots were trained to extend the flaps before reaching their critical Mach number, which prevented the violent dives that had destroyed so many earlier Lightnings and cost the lives of their pilots. When the Luftwaffe realized that P-38s could now follow them through dives, they were stunned. For 3 years, the split-S escape had been their fallback option, a tactic that had saved countless German aviators. Earlier P-38 models without flaps, such as the J-10 or J-20, could be shaken off easily in a dive. But the arrival of the J-25 changed everything. German technical teams later studied a wrecked P-38 and discovered the flaps. But by late 1944, the situation in Germany made any countermeasure impossible. Constant bombing raids, collapsing production lines, and shortages of vital resources prevented the Luftwaffe from making similar upgrades. The introduction of dive recovery flaps was more than just a minor modification. It shifted the entire dynamic of the air war. Fighter group reports showed a sharp drop in German escape rates once the new P-38s arrived. For years, German pilots had been confident they could break off combat at will with a split-S dive. Now P-38 pilots could follow them through any maneuver. The psychology of battle flipped. The hunters had become the hunted. Back in late 1943, several hundred field modification kits had been produced to give squadrons in North Africa, Europe, and the Pacific a fighting chance against compressibility. The kits showed the adaptability of American industry. At Lockheed's Burbank plant, crews could install dive flaps in just a few hours. In England, field units eventually received kits through safer delivery routes after the loss of the C-54 transport. Even so, production delays meant that only about half of all P-38s built ever received dive flaps on the assembly line. The program added to American understanding of transonic flight. Engineers spent 17 months gathering flight test data and pilot reports before they understood exactly why the Lightning's nose dropped in dives. That knowledge helped lay the foundation for supersonic aircraft development after the war. The dive flap project showed America's advantage, solving problems step by step and applying improvements quickly, while Germany often focused on radical new designs like jet fighters that took far longer to produce. In the Pacific, the Lightning truly came into its own. Most air battles took place below 20,000 ft, 6,080 milliliters, so engine issues and cockpit heating problems that plagued Europe were not a factor. Compressibility was less of a concern at those altitudes, but the dive flap still gave a crucial edge. P-38 pilots could pursue Japanese fighters through any maneuver, making the Lightning one of the most feared aircraft in the theater. Major Richard Bong, America's top ace with 40 victories, flew only P-38s in the Pacific. Most of his kills came before receiving aircraft equipped with the new flaps. But the upgrade made the already dominant Lightning even more effective against Japanese planes. The dive recovery flaps were an elegant piece of engineering. Each flap measured roughly 18 by 35 inches, mounted just outboard of the engines on the wing's underside. When extended, they disturbed the airflow just enough to prevent the dangerous shift of lift to the rear of the wing. Clarence Kelly Johnson and his team at Lockheed had worked tirelessly to troubleshoot the Lightning's issues. When Japan attacked Pearl Harbor, only 69 P-38s had been delivered to the U.S. Army. The pressures of war accelerated development, and the dive recovery flaps were one of the clearest examples of American ingenuity under pressure. For the Luftwaffe, the loss of the dive escape meant a complete change in tactics. German pilots were forced into turning battles where the Lightning's concentrated firepower, 4 50 caliber machine guns and a 20mm cannon mounted in the nose, could tear through enemy aircraft. The air war over Europe would never be the same. The effect on morale was dramatic. For years, German pilots had trusted the steep dive as their last safe option. Once the P-38s received dive recovery flaps, that safety net disappeared. Suddenly, what had been their guaranteed escape became a trap. This loss of confidence weakened the Luftwaffe's effectiveness during the final months of the war. The dive recovery flap program left behind detailed records that became invaluable after 1945. Every flight test, combat trial, and modification was carefully documented. These reports established core principles of high-speed flight control that shaped aircraft design for decades. While the P-38's nose drop in compressibility was never completely eliminated, Lockheed's solution in 1944 gave pilots the ability to hold control during high-speed dives. The flaps worked by slightly slowing the aircraft and restoring elevator authority. Their quick development and fielding highlighted America's industrial strengths. From the moment the problem was identified to the point where combat units had the fix, only 16 months had passed. Germany, by contrast, lacked the resources and stability to attempt such rapid changes in 1944. Lockheed also showed flexibility. Production lines kept moving while workers modified aircraft with the new equipment. Installations happened both on the assembly floor and in field conditions, allowing frontline units to get the upgrades as quickly as possible. Combat reports made the difference clear. Before the flaps, most German fighters broke away safely when they dove from a P-38. Afterward, escape rates plummeted, and P-38 scored more kills in situations that once would have ended in frustration. Many American pilots survived dives that would previously have claimed their lives. No longer forced to break off a chase, they could press the attack to the end. The impact extended beyond the Lightning. Republic Aviation applied the same idea to late production P-47 Thunderbolts. Lessons from the program carried over directly to transonic research, helping engineers prepare for the jet age. Analysts later concluded that the dive recovery flap program generated more useful data on compressibility and transonic flight than any other wartime effort. Every P-38 pilot who used the flaps added to that knowledge base. By autumn 1944, more P-38s in Europe had received the upgrade, and the results were soon visible. During Operation Market Garden in September, large-scale air battles over Holland gave the Lightning a chance to prove itself. The Luftwaffe threw in some of its best surviving units to stop the Allied airborne operation. With the new flaps, P-38 pilots followed German fighters through every dive and evasive move, achieving kill ratios that would have been unthinkable months earlier. The success continued into the winter of 1944-45. On January 1, 1945, during Operation Bodenplatte, the Luftwaffe's last major offensive, P-38s intercepted German fighters retreating from attacks on Allied airfields. Pilots who planned to dive away found Lightnings still on their tails. The ability to maintain contact during dives contributed to the heavy losses the Luftwaffe suffered that day, losses from which it never recovered. The influence of the flap research went further than World War II. Early jet programs built directly on the findings. When Chuck Yeager broke the sound barrier in 1947, the Bell X-1 used a variable stabilizer system derived from P-38 compressibility studies. What engineers had learned about shock waves and pitch control with the Lightning became essential to designing aircraft that could safely cross into supersonic flight. The numbers proved the program's worth. The dive recovery flap project cost about $8 million in 1944. Analysts estimated it saved around 260 P-38s from being lost to compressibility between August 1944 and May 1945 based on earlier accident rates. With each Lightning valued at $97,000, the hardware savings alone exceeded the investment. Adding in the survival of trained combat pilots and the increase in enemy aircraft destroyed, the program paid for itself many times over. The flaps also changed pilot training. The Army Air Forces revised their curriculum, requiring new instruction on flap use. Standard practice was to deploy the flaps at 450 mph indicated airspeed or at the first signs of buffeting. Pilots were taught to keep the flaps extended for at least 3 seconds before pulling out of a dive to avoid damaging the airframe with sudden deceleration. Training proved highly effective. Crews who learned proper procedures had far fewer accidents than those flying unmodified P-38s. Germany attempted answers, but none reached the front lines. Focke-Wulf engineers tested spoilers on the wings of the Fw-190D, with promising results. But the idea never entered production. Messerschmitt considered variable incidence tailplanes for the Bf-109K, and even built prototypes in early 1945, but the war ended before any operational use. The Me-262 jet fighter, which began service in mid-1944, avoided compressibility through its swept-wing design, yet only about 1/400 were ever produced, too few to solve the Luftwaffe's larger problem. Part of the P-38's advantage came from secrecy. The Americans managed to keep the development of dive flaps hidden until they were in combat. Despite German intelligence networks and spies in neutral countries, the program remained secure. Lockheed enforced strict internal measures, including separate storage of design drawings, limited pilot briefings, and additional non-disclosure agreements for workers. As a result, the Luftwaffe had no warning until their old tactics suddenly failed in the skies over Europe. The arrival of dive recovery flaps permanently altered the air war. German fighters could no longer depend on a maneuver that had saved them time and again. For the Allies, the P-38 Lightning emerged stronger, safer, and far more deadly than before. American pilots quickly adapted to their new advantage. With dive recovery flaps installed on the P-38, they no longer had to break off pursuits. They pressed their attacks with confidence, knowing German fighters could not simply dive away to safety. This change in combat tactics hit the Luftwaffe at the worst possible time. Their veteran pilots were already dwindling, and once their most reliable escape method was gone, losses mounted at a pace Germany could not replace. The result was a steady decline in air power that helped secure Allied superiority in the skies during the final year of the war. The importance of dive recovery flaps was officially recognized after the conflict. The United States Strategic Bombing Survey listed the loss of the dive escape tactic as one of the top reasons for the Luftwaffe's collapse. Interviews with German veterans years later confirmed this view. Many admitted the shock of facing P-38s that could now follow them into dives completely changed their outlook. They had trained for years believing dives guaranteed escape, and suddenly that belief was shattered. Forced to improvise with weaker alternatives, they lost both confidence and effectiveness. Today, surviving P-38s with their original dive recovery flaps stand as reminders of that wartime breakthrough. Museums proudly display them, often with the flaps extended to show visitors how such a small feature could alter the balance of combat. At the Smithsonian National Air and Space Museum, complete technical records are preserved. These include wind tunnel data, design notes, combat reports, production blueprints, and even instructions for field modifications. For engineers and historians, this archive is still a vital resource. The dive recovery flap program is now taught in aerospace engineering courses and military academies. Students examine both the technical solution and the organizational lessons it represents. They learn the value of clearly defining a problem, the power of simple fixes over overly complex ones, and the importance of speed in implementation. The program stands as proof that rapid innovation under pressure can shift the course of a conflict. Behind this achievement were individuals whose commitment made success possible. Kelly Johnson worked relentlessly to understand compressibility and design a solution. Test pilot Tony LeVier risked his life proving the flaps worked at combat speeds. Engineers like Ward Beeman and Carl Hayden built reliable systems despite tight deadlines. Assembly line workers fitted the modifications outdoors in all weather to keep production moving. Maintenance crews in the field installed kits under combat conditions. Each step of the chain mattered, and together they delivered an innovation that saved lives and shortened the war. Modern fighter jets still reflect lessons learned from the P-38's dive recovery flap experience. Today, fly-by-wire systems automatically adjust control surfaces at high speed, accomplishing electronically what mechanical flaps did in 1944. Materials have changed from aluminum plates and electric motors to composites and processors, but the principle remains the same: maintaining control when speed threatens to overwhelm it. While dive recovery flaps alone did not win the air war, they stripped the Luftwaffe of its last dependable defensive move at a decisive point. Combined with America's numerical advantage, stronger pilot training, and Germany's growing fuel shortages, the modification accelerated Germany's downfall in the skies. Timing mattered greatly. If the program had been delayed by even 6 months, German jets like the Me-262 might have appeared in numbers large enough to balance the advantage. Instead, the flaps ensured Allied dominance through the decisive final campaigns. The dive recovery flap program became a textbook example of wartime innovation. It showed that success often came not from futuristic wonder weapons, but from practical improvements to existing systems. Lockheed engineers and American industry proved that flexibility, rapid testing, and fast production changes could outpace enemy responses. This model of problem-solving shaped American military development for decades after the war. The story of the P-38's transformation highlights how small changes can produce large results. With 2 aluminum plates and an electric motor, engineers solved what many thought was an unsolvable flaw. The P-38 shifted from a fighter with limitations to one capable of dominating its opponents. German pilots who had relied on steep dives for 3 years suddenly found no escape. The shock of being pursued through maneuvers once considered safe accelerated the Luftwaffe's decline when Germany could least afford it. The P-38 service record has been debated, but context matters. Engine problems at high altitudes mostly affected the 8th Air Force, where early G and H models suffered from cooling issues. The later P-38J and L models, however, performed with great success over Europe from Italian bases at every altitude. With dive recovery flaps correcting the final major weakness, the aircraft became a complete and effective weapon. Germany, meanwhile, invested in advanced projects that rarely reached meaningful production. America instead perfected practical fixes that worked immediately. From the first ideas at Lockheed's engineering office to operational P-38s in European skies, the dive recovery flap program proved the strengths of American problem-solving, industrial adaptability, and speed of execution. The long-term legacy is clear. Every modern fighter designed to stay controllable at extreme speeds carries lessons drawn from the P-38 program. Every aerospace engineer who learns to pursue simple, direct solutions studies its example, and every military historian recognizes it as a turning point in air combat. German intelligence never anticipated that such a simple change could erase their best tactic. They underestimated the ability of American industry to design, test, and field a solution before they could react. And they never expected P-38s that once fell behind in dives to suddenly follow with full control. Those modest aluminum flaps marked the difference between escape and destruction, survival and loss, tactical edge and collapse. They proved that sometimes the most decisive weapons are not the most complex, but the simplest solutions to the right problem. By the time the Luftwaffe realized this, it was far too late. What had been their sanctuary in the sky became a trap. The dives that once meant safety now led only to defeat. As P-38s pressed attacks with deadly precision, the hunters had become the hunted, and air combat over Europe would never be the same.